Assalamualaikum. Hi everyone. Let's discover chapter 3, electrochemistry. There are 3 subtopics in electrochemistry. 3.1 Galvanic cell, 3.2 Nernst equation, and 3.3 electrolytic cell. The learning outcomes for subtopic 3.1 are: what is electrochemistry? Electrochemistry is the study of the relationship between electrical work and chemical change. There are 2 types of electrochemical cell: galvanic cell and electrolytic cell. Galvanic cell is chemical energy changed to electrical energy, while electrolytic cell is electrical energy changed to chemical energy. Let's flashback what we had learned for SPM. This diagram shows an example of galvanic cell. How do you determine which metal belongs to which electrode? What is electrode potential? Electrode potential is a measure of ability of a half cell to attract electron towards it. Indicates how easily a half cell undergoes a reduction. Also indicates how much voltage will a half cell produce. This is an experimentally determined value. Example, this is a half cell. Cl2 plus 2 electron produce 2 Cl minus. The E naught is positive 1.36 volt. Ag plus electron produce Ag. The E naught is positive 0.80 volt. Al3 plus 3 electron produce Al. E naught is negative 1.66 volt. This is the value of electrode potential of each half cell. This is the table of standard reduction potential, SRP. The more positive value, the easier to reduce, meaning that the chemical reaction is occur at cathode. The more negative value, the easier to oxidize, meaning that the chemical reaction is occur at anode. Don't memorize all this value because it is given in the questions. This mnemonic was built based on SRP. For matriculation level, the value of SRP will be given in the question. To be easy, remember this. NOx. Oxidation is lost at the anode. Red cat. Reduction is gained at the cathode. Lower E naught value will become anode electrode and undergoes oxidation. Higher E naught value will become cathode electrode and undergoes a reduction. Galvanic cells are built up from 2 electrodes, anode and cathode, 2 electrolytes, salt bridge, and voltmeter. The electron is flow from anode to cathode. Construction of galvanic cell. A galvanic cell, also known as a voltaic cell, is an electrochemical cell that uses spontaneous redox reactions to generate electricity. It consists of two separate half cells. A half cell is composed of an electrode immersed in a solution known as electrolyte containing ions of the same metal. These two electrodes are connected by a wire through external circuit. The solutions are connected by a salt bridge which allows ions to transfer but does not allow the solutions to mix directly. The salt bridge completes the electrical circuit. There are two electrodes in a voltaic cell, one in each half cell. Anode. The anode is where the oxidation reaction takes place. Metal electrode lost electrons. An anode become negative electron. While cathode is where the reduction reaction takes place. Metal electrode gains electrons and cathode become positive electron. There are two types of electrode, active electrode and inactive electrode. What is active electrode? Active electrode is an active component in its half cell and is a reactant or product in the overall reaction. While inactive electrode provide a surface for the reaction and completes the circuit. It does not participate actively in the overall reaction, meaning that inactive electrodes are necessary when one of the reaction components can be used as an electrode. Inactive electrodes are usually unreactive substances such as graphite or platinum. This is an example, a galvanic cell using active electrode, copper half cell and zinc half cell. Based on the value of the standard reduction potential, copper has more positive E0 than zinc. Therefore, copper favors a reduction process and become cathode. Hence, zinc will be anode electrode and undergoes oxidation process. Look at this diagram. In zinc half cell, zinc electrode is immersed in zinc sulfate solution. In copper half cell, copper electrode immersed in copper sulfate solution. Zinc electrode is anode because zinc oxidized to zinc ion. The electron flow from anode to cathode through the external circuit. So, anode is negative electrode, cathode is positive electrode. At copper half cell, copper ion undergoes a reduction forming copper solid. During the chemical reactions occur at galvanic cell, what happens at anode and at cathode? At anode, oxidation occurs. The zinc electrode slowly dissolves. Zinc metal lost its electrons and it is oxidized to zinc ion. Observation is zinc metal become thinner. While at cathode, the reduction occurs. The electron from the zinc metal flow through the wire, enter the copper metal and taken up by copper 2 ions. Copper ions accept the electrons and it is reduced to copper solid. The observation that we can see is brown solid is deposited on the copper electrode. This reaction shows the redox reaction in galvanic cell. Redox reaction involve both oxidation and reduction that occur simultaneously. At anode, zinc is the reducing agent. It lost electron and undergoes oxidation to become zinc ion. The oxidation number increased from 0 to +2. At cathode, copper ion is the oxidizing agent. It accepts electron and undergoes a reduction forming copper. The oxidation number decreased from +2 to 0. Cell notation is shorthand description of galvanic cell. We can apply ABC rule in writing the cell notation. A is reaction at anode on the left. B is short bridge in the middle and represented by double line. C is direction at cathode on the right. Single line represent different phases, comma for same phase. Concentration of electrolyte must be written in bracket. If all the substances involved are aqueous or gas, a platinum or graphite electrode is indicated. A galvanic cell using inactive or inert electrodes. Example, based on the value of the standard reduction potential, Mn2 plus half cell has more positive inert than I minus half cell, meaning that Mn2 plus half cell favors the reduction process and become cathode. Hence, I minus half cell will be anode electrode and undergoes oxidation process. This diagram shows a galvanic cell using inactive or inert electrode. At anode, an inert graphite electrode is used for the half cell containing I- ion and I2 solid. Iodine cannot be an electrode even though it is solid because iodine is species that easily dissolve in electrolyte. At cathode, as for Mn2 plus half cell, a graphite electrode is also used since there are only aqueous solution involved. This is the half cell equation at anode and cathode. The anode half cell in the cell notation is written in this way. Single vertical line is used to separate substances of different phase. For cathode half cell, comma is used to separate two different ions of same phase in the cell notation. All the electrodes are written at both ends cell notation. For a galvanic cell using active and inert electrodes, the example is based on the value of the standard reduction potential, Cl2 half cell has more positive inert than zinc half cell. Therefore, Cl2 favors a reduction process and become cathode. Hence, zinc will be anode electrode and undergoes oxidation process. This diagram shows a galvanic cell using active and inert electrodes. At anode, for zinc half cell, zinc is used as electrode because it is active electrodes. While at cathode, for chlorine half cell, a platinum electrode is used since there are only gas and aqueous solution involved. This is the half equation at anode and this is the half equation at cathode. To write down the cell notation, apply ABC rule, which is A is the reaction occur at anode. Use vertical line to separate zinc solid and zinc 2 plus aqueous. Use bracket in writing concentration of zinc 2+. B is salt bridge in the middle and represented by double line, while C is direction occur at cathode. Use vertical line to separate Cl2 gas and Cl- aqueous. Use bracket in writing pressure of Cl2 gas and concentration of Cl- aqueous. The electrode used at cathode is platinum or graphite because only gas and aqueous solution involved. All the electrodes written at both end cell notation. Salt bridge is an inverted U-tube containing a gel permeated with solution of an inert electrolyte such as KCl, Na2SO4, and H4NO3. The function of the salt bridge are help to maintain electrical neutrality, to complete the circuit by allowing ions carrying charge to move from one half cell to the other. Without the salt bridge, positive and negative charge will build up around the electrodes, causing the reaction to stop. How does the cell maintain its electrical neutrality? In inert half cell, as oxidation occurs, zinc ions enter the solution, causing an overall excess of positive charge in the solution. As a result, ions in the salt bridge move to the zinc half cell to balance the charge. In the cathode half cell, copper ions are attracted to the cathode to undergo reduction. Copper ions leave the solution, causing an overall excess of negative charge. Therefore, K-ions from the salt bridge move to the copper half cell to balance the charge. So, the electrical neutrality is maintained. A closer look at the electrodes. In inert half cell, oxidation of zinc to zinc 2+ leaves electron behind on the electrode. Solution becomes more positive. In the cathode half cell, reduction of copper 2+ to copper, electron extracted from electrode. The solution becomes more negative. What happens if there is no salt bridge? As the zinc rod dissolves, the concentration of zinc 2+ in the left beaker increases. So the reaction stops because the net increase in positive charge is not neutralized. This excess charge built up can be reduced by adding a salt bridge. Standard hydrogen electrode, She. Describe the method used to determine standard electrode potential. She is a half cell served as a reference to determine the standard electrode reduction potential of other half cell. The standard reduction potential of a half cell is determined by pairing that half cell with She. This diagram shows a standard hydrogen electrode, or She. It is made up of a platinum electrode coated with finely divided platinum, which is acted as catalyst for the half cell reaction. Platinum electrode is immersed in an aqueous solution of hydrogen ion. The concentration is 1 molar. Usually, hydrochloric acid is used as aqueous solution, and it bubbles with hydrogen gas at 1 atm pressure and the temperature at 25 degrees Celsius. The value of the standard reduction potential of She is 0.00 volt. She is used as a reference electrode with standard reduction potential of 0.00 volt. She can act as either cathode or anode when connected to other half cells. Electrode with more positive standard reduction potential value act as cathode. If the standard reduction potential for the half cell is negative value, the half cell electrode is anode and She is cathode. If the standard reduction potential for half cell is positive value, the half cell electrode is cathode and She is anode. Measuring standard reduction potential of zinc when She as cathode. Standard reduction potential of zinc half cell is measured by setting up the electrochemical cell as below. When the circuit is closed, the following observation can be made. The voltmeter reading in not cell is 0.763 volt. As the cell operates, the mass of zinc electrode decreases and concentration of zinc 2+ ions increase in the solution, meaning that zinc half cell undergoes oxidation at anode. The concentration hydrogen ion decrease in the She. Gaseous hydrogen is produced, means that She undergoes reduction at cathode. At anode, zinc half cell undergoes oxidation. At cathode, She undergoes reduction. To write the cell notation, don't forget to apply ABC rules. A. Direction is occur at anode. Use single vertical line to separate zinc solid and zinc 2+ ion. Use bracket for concentration value of zinc 2+ ion. At anode, zinc is act as electrode because it is active electrode. At the middle, short bridge is represented by using double line. C is direction occur at cathode. Use single vertical line to separate hydrogen ion and hydrogen gas. Use platinum as electrode because direction at cathode only gas and aqueous solution involved. Standard reduction potential of zinc half cell can be determined from this formula. E naught cell equals to E naught cathode minus E naught anode. At cathode, She undergoes a reduction. At anode, zinc half cell undergoes oxidation. The value of E naught cell is taken from the voltmeter reading. The value of She is 0. Then, the standard reduction potential of zinc half cell can be determined. Negative 0.76 volt. How to measuring standard reduction potential of copper when She as anode. Standard reduction potential of copper half cell is measured by setting up the electrochemical cell as below. The voltmeter reading is 0.337 volt. When the circuit is closed, the following observations can be made. The voltmeter reading in not cell is 0.337 volt. As the cell operates, mass of copper electrode increases and the concentration of a Cu2+ ions decreases in the solution. Means that copper half cell undergoes reduction. Gaseous H2 is consumed. The hydrogen ion concentration increases in the She, means that She undergoes oxidation at anode. At anode, She undergoes oxidation. At cathode, copper half cell undergoes reduction. And to write the cell notation is like this way. To calculate the standard reduction potential of copper half cell, use this formula. E naught cell equals to E naught cathode minus E naught anode. Copper half cell occur at cathode. She occur at anode. The value of E naught cell is taken from the voltmeter reading. The value of She is 0. So, standard reduction potential of copper half cell can be determined, which is positive 0.337 volt.